In the previous video, we looked at MLOps. What are the steps involved in MLOps? What gets managed? We also took a look at one such tool which is very popular for MLOps, which is called as MLflow. That's an open source tool. In fact, MLflow is actually one part of the puzzle, right? When you start using MLOps in production, rather than MLOps in practice, the three things that get managed, right, which is models, code, and data that the model is actually trained on. The ML flow helps with the what models, how do you manage them, how do you deploy them, etc. How do you track the versions in production. The code itself is something that you have to use a versioning system. That versioning system is typically something like GitHub, right? You can use that for the code changes and version controls around that. And then for data, you end up using versioning systems for data itself, right? That really comes down to your best practices in data management. Now, if the data is actually not changing, the data is always getting appended to, then there isn't much of a problem there. You just keep adding all of those appends into a table and then keep track of when did this particular append happen. Whereas if you have data that gets changed as a result of pipelines that execute earlier, then you might want to keep track of the change itself, right? What value was there before, what value is inserted now. Basically, that's similar to that slowly changing dimension type 2 table structure that we spoke about earlier in one of the week to week videos. So yeah, data changes also have to be versioned. So make sure that you do the data management for it properly. Why is that important, by the way? So if you have, let's say, features that you build, and these features are built by pipelines that you write, and those features end up becoming the independent variables on which the models are trained. Let's say the features now change. Why did the change happen? Maybe some genuine logic change could have happened, or some new correlations were found. Either which way, the value of a particular feature could change, right? Or you could have new values coming into play, or the meaning associated with the value of a feature could change. Let's say, for instance, you do one-hot encoding, right, as an example. And that's a feature which of engineering that you do for a categorical variable. Now, you could have just three classes, in which case the one-hot encoding is just maybe like a 3-bit array. But then as the classes increase, now you have more and more values coming in. So the one-hot encoding becomes tedious after a point in time. So then you start to consider maybe a dictionary encoding. And the dictionary encoding is more efficient from a space perspective. But that's a completely different way to encode compared to one-hot, right? So at that time, the model might also change in terms of how it picks up the distances between that encoded value compared to the previous one-hot encoding version. So that could result in a different model with different parameters as being the optimal version that gets promoted to production. So all kinds of things start happening, right? Just because you changed the data in the backend. So that's why it's important to keep track of all three. The environment itself changes. We spoke about the need for segregating between dev, staging, and production. Let's spend a bit more time on that to understand why that's the case. See, in practice, the production data, which is basically the most sacrosanct of data, is not available anywhere else. So you might have large amounts of data sitting in production, and you might not have access to it while you build a model. So then what you have to go with is some replica of the production data, which is kind of mirroring the production data, but not exactly. So one standard technique that many companies use is, I'll take the same data as in production, but then remove all the PII information. PII stands for personally identifiable information. So if I remove all the PII and then give you the data, potentially you could still train your model as long as the models don't have the PII fields themselves as the independent variables on which the models need to be trained. So as long as that doesn't happen, the models that you train using the rest of the data could still be valid. But in practice, what happens is nobody that I've seen actually has a good enough copy of production data in another environment. Even like some of the biggest banks that we end up working with, biggest telecom companies, they don't have access to that exact same data. So what ends up happening is they end up giving data from test environments, and oftentimes the test environment data is corrupted. meaning that the data itself is getting produced as a result of other test runs because the test environment doesn't have the same sanctity that the production environment has, and therefore the data being not of good quality ends up corrupting the rest of the data which could be of good quality. So one rotten apple spoils the basket types, right? So that ends up happening all the time. But sometimes it's even more simpler reasons, which is they just don't have the mechanisms to bring production data in. So then what ends up happening is you end up mocking what could the data look like, right? Mock data gets created. And mock data is notorious for having very different behavioral characteristics from what is actually, in real life. So you could have correlations in mock data, but those correlations don't exist in production. And it could be the vice versa, right? So what ends up happening, therefore, is you cannot trust the data that's available in other environments other than production. So if that's the case, would you then be comfortable training a model on data that's not sacrosanct, not of high sanctity, not like production, in another environment, taking that model and saying that model is my most optimal model for solving the problem statement, and then promoting the model to production? You would not be comfortable doing that, right? Because the model that you produce might be wrong in the first place because the data is not correct. So what therefore is best practice is not just to have environment separation, but also to promote code and not models, right? So then when you look back on the different things that you track, the code that you promote is what's actually important, right? To make sure that you do that correctly, diligently, etc. The data is of course not under your control. In production, the data is typically managed by like a data governance team or a data office, and hopefully they're doing the right thing. If not, you can give them inputs. And then for the models that get produced in production, which means the models get trained in production data, the models get deployed in production, and then there could be like challenger models, champion models, etc. Basically, current model, but new models getting changed as a result of better algorithms, better parameters. Either which way, all of those models, all of those changes get tracked to MLflow. That's how you should think about it. Now, the staging environment plays another crucial role, which is it allows you to package a bunch of things together now. Right? In dev stages, typically on a notebook in your laptop, you would not really worry about changing data. You would just worry about the current version of the data that exists and the features that you need, the algorithm that you need to choose. Right? Those are the things that you end up focusing your energies on in the dev cycle, in the dev environment. Once you're ready, once you're confident that a particular algorithm choice is going to be potentially the best performing, then when that code, right, gets shipped to staging, that's when you start paying attention to changes in the data, right? Notice that production data may not be available at staging typically, but the schema of the data, which is the metadata, and the schema of the features that you're building, all of those are available to you on the staging side. So in the staging environment is where you start working with the interdependencies between data and code. So then you start to worry about, okay, so if I make some changes to the features, which version of the feature is going to be used for a particular model run? All of those get decided at this stage. So once you're ready with that, that means there is some change in the data, in the way the features are engineered, etc., which is again code change, right? And then once you get into production, the code of all of that goes into production, right? The code for data, the code for feature engineering, the code for the model execution, not the execution, model training firstly, and then the code for the model execution. All of that goes into production through like a versioning control system like Git. So in production, you go compile the code, you go run the code, deploy the code, etc., etc. So then that becomes the way to go about it. If you didn't have staging, you'd go directly from dev to production, and you might actually break the dependencies that came about because of data-related changes that you didn't catch in dev. So environment separation is critical. Obviously, you also cannot run dev code in production directly. Right? That doesn't make sense. So that's another reason why separation of environment is also useful to segregate production environments from impact of bad code or bugs or the entire development process. Yeah, so we spoke about promotion of code and not models because that's what ends up being foolproof. Now, when we talk about deep learning, we'll come back and take a look at this best practice. Because in the case of deep learning, when you start looking at model training at very large scale, maybe there are better methods, right? There are better approaches in practice, because you can't just take code and start training it all over again in production. That might be a bit of a problem, or it could take a long time. So there are ways around it. We'll talk about it when we talk about deep learning. Great. So let's put everything together that we learned about big data machine learning. So first and foremost, it's important to think in terms of managing the machine learning exercise, just like you would manage software. So MLOps is a critical factor. So that's MLOps is going to become a common thread across all of the steps that you see here, right? But let's just keep that in mind. As one of the first things that you do, like with all machine learning, you do feature engineering, right? To get the data in a particular shape, you get the features that you want to create independent variables. But because the data set is large in size, you end up doing feature engineering using data engineering pipelines written in Spark, right? That's one of the main reasons why we learn Spark in this course, right? That's why you took this course in the first place. Now, that's just the first step. The code that you write as part of it, you obviously check it into Git and make sure that it has version control applied to it. The data that you engineer, the features that you engineer, make sure that that's getting versioned correctly, and any changes to the interpretation, to the semantics of it, any new columns that you introduce, all of that should be part of data versioning systems. Okay, then comes the model training and selection, and here you want to choose between algorithms which are parallelizable, right? So we spoke about that concept as well. So anything which has that statistical query model is suitable for this parallel execution using divide and conquer. So pick from one of those algorithms. You don't need to worry about which algorithm is the right algorithm. If you use AutoML, right, automated machine learning, which is basically automated model training, that's available with Spark as well. That's available with other systems. But then, if you choose that, then you need not worry about which algorithm is getting chosen. It's going to end up choosing the right thing based on the underlying distribution of the data versus the prerequisites that the models themselves have. Then once the model is trained and selected, then you publish the model, right? Which is basically you create a serving interface, right? So this publishing or this deployment could be like a pickle file, it could be a container, could be like an API, right? Again, use MLflow, right? In this process. Then you start scoring the model, and here the model scoring is typically an activity that happens automatically as part of a pipeline, as part of an application. So usually model scoring is online, meaning one model invocation at a time, and potentially it's also high concurrency, right? So this is actually an OLTP kind of a workload. So if you take a look at credit card fraud systems, right? So credit card fraud systems end up doing checks on when did the credit card gets used last, what is the characteristic of its usage, and is it deviating from the normal usage of the credit card, in which case it flags an anomaly, and then there's an alert sent out, there's an SMS that goes to you saying, did you use your card at this particular place? We think it might be stolen, etc., etc. So those are actually outputs of model invocations. But the critical part is that the model needs to make up its mind whether something is potentially fraudulent or not in real time, like in a jiffy. And when it needs to do that, it needs to run for every single credit card transaction. And imagine doing this at the scale of MasterCard or Visa, right, which is very, very large in terms of network. So that's a very, very big, OLTP kind of workload. So that needs to also be factored into the model scoring exercise. Yeah, so the model scores need to be captured. Basically, those become the results of the model. And then that gets logged as part of the model invocation. So again, MLflow. Think about it that way. Now, once these things are in production for some period of time, the data could change, right? The characteristics of the data do change. So this is called as drift, right? And whenever there is a drift, you don't want to be caught unaware, right? You want to be aware of it. You want to be able to take some action based on that. So what you set up there as a result is something called as drift detection. So effectively, you want to monitor for certain parameters in the data and see whether those parameters are changing. So simple examples could be you're expecting a certain volume of data on a regular basis, let's say on a daily basis, and suddenly the volume is changing, which means maybe the business has changed, maybe there is an anomaly, there's a skew, or maybe there's a case of bad data, who knows. But at least you have to take some action is what is known. So that could be a simple thing, right? The other common thing that's possible would be you correlate between the variables that you're interested in. And those variables themselves are coming in from source columns. So you check for the columns, you check for the quality of the columns, and then you compute the correlations and ensure that the correlations are as per what you took in the initial step when the model was trained and deployed. So if it's not, then you have to go back and change the model, right? So that could be another example. The third example could be there's maybe an underlying distribution to the data, and you're ensuring that you make some assumptions which are based on the underlying distribution such that you coded the final model. So if those assumptions are not true anymore because the underlying distribution has changed, then it's a problem. So the example here is you could be making, let's say you built an anomaly detection model and you made an assumption that all of the errors that come in are extremely sparse and are distinguishable from the main data, right? By two standard deviations from the normal. So why two standard deviations? Because that's something you looked at empirically given the past data. But then there could be some changes in the data characteristics that made errors possible even within one standard deviation, right? That could be the new business model, in which case you are not going to be able to detect those errors, and then those errors might slip your attention, etc., etc. So those kinds of issues can crop up. So drift detection is an important step. You have to think about that as part of your model exercise, and you make sure you come up with clean definitions that are codable, automatable, and you put those into production. So remember, what you're tracking the drift is in the production data, not dev data, not UAT staging data, but in the production data. So therefore, right, the code that you write for drift detection also has to go through the same version control with Git, right? So that it goes into, it goes through the same rigor and gets managed. Then once the drift is detected, let's assume some drift is detected, like let's say 6 months after the first model went live, then you need to take some action. Typically, the action that you take is retraining, right? The code remains the same. Typically, the code does not change. Right? It depends on the drift, of course. Let's assume the drift is just more data, right? Or more volumes. Then the nature of the data has not changed, so therefore no change in the code as required, but you just need to retrain the model, which means the parameters need to be chosen again. The right algorithm needs to be chosen again. So again, you use Spark with AutoML potentially, and then the retrained model gets generated. What you don't want to do is push that as the final answer. You want to start doing comparisons, right? Of course, evaluation matrices are good, right, for certain kinds of models which are easy to understand and compare, like for instance reference scores. But there are other kinds of models where historical data performance alone is not enough, right? You need to be able to run this live in parallel, in conjunction with the current model that exists, and then measure the efficacy. So one example of this is recommendation engines, right? In the case of a recommendation engine, while you use historical data to train, the efficacy, the impact of the recommendation engine really comes from being able to do the recommendations live compared to the previous way of doing recommendations, or the do nothing way of recommendations, which is basically not recommending at all, just doing random recommendations. So that kind of a setup, you would basically create an experiment that's called as an A/B test, right? And then pick up your new model that you've trained, and let's call that the challenger model. What is it challenging? It's challenging the champion. The champion is already live in production. It's kind of like the boxing analogy, right? There's a champion and then the challenger comes and challenges him to a fight, and then they end up fighting, and then the winner is chosen. Like that. Here, the analogy to the fight is basically what's called as an A/B test. What you would do is that in production, you would take the online data from the applications and then direct it, right, to either the champion or the challenger or both, and let them make a choice, let them score, let them do the recommendations, or let them do whatever it is that they're doing, and then look at the results from it, and then compare the results, right? A champion would produce a certain result, a challenger could produce the same result or even better, controlled for natural variations, right? That's possible. Because a challenger model is being trained on newer data, remember that, right? So some natural variation is expected. So controlled for the natural variation, despite the control, the challenger performs way better. If that's the case, then you want to promote the challenger and demote the champion. When that happens, you don't want to overwrite the champion into the same API, right? While that's possible, the better approach is to actually create versioning again, right? The new version of the model gets assigned to the challenger. The older version continues with champion. The champion part of the endpoint is taken down. The challenger model is mapped to the API, the final endpoint that the API has, and then the code continues running. Now, it could be the case that like maybe a week later or 2 weeks later, you might have to roll back because the challenger model suddenly you realize that some crucial assumption is missing. When that rollback happens, if you overrode the champion model, then you'll have to go pick it up from the ML flow model registry, right? Assuming that exists. If it doesn't exist, then where you go pick it up from? You pick up the challenge. So by versioning and by having Git as well, right? You get access to that version of the model that was running at that particular point in time in the past, even though you've had multiple challengers come in after that got promoted, right? So again, ML flow, Git, those become very critical storehouses of versioning. And then finally, once the challenger model is done, the entire cycle starts all over again. Because sometimes you might have to start from feature engineering all over because the drift is too high, or new data sets have been added, new approaches are possible, etc. So in practice, a machine learning exercise is never ending, especially in big data, because the data is very large. You might have to constantly be on your tiptoes, figuring out what's changed. You may not notice patterns in the smaller scale, you might notice patterns in the large scale. So these become like a constant activity. In a big company setting, a lot of what I just talked about is actually done by what's called as an ML engineer, right? An ML engineer actually does not do ML. They do more the engineering aspects of ML, which is basically MLOps, feature engineering and stuff like that. But in my view, that's too much of a specialization, right? I would rather that the data scientist actually picks up the knowledge about big data engineering, MLOps as well, because it's core to how the model gets produced, right? And therefore, it has to be intrinsic knowledge that the data scientist has. With that, we come up to a close with this week's lectures. So hope you enjoyed about learning about big data at large scale, machine learning at large scale, and then you get to apply some of these techniques in practice, hopefully. Thanks.